Yes, Sai, you may start it now.
Yes, ma'am. So about superconductivity. Now, before I start with superconductivity, I would just like to revise, do a kind of a recap like thing about how materials can be we have seen that materials can be classified as um, conductors, semiconductors, and insulators based on their conductivity or resistivity. And here in this slide, I have also shown the conductivity and resistivity of all the three types of materials. So the conductivity of the conductivity of the conductors starts from 10 raised to 10
Sai,
raised to 6. Yes, ma'am.
Sai, just
Yes,
can
ma'am.
you keep it on a presentation mode? Your
Yes, ma'am.
slide.
Yes, ma'am. Ma'am, is it okay?
Just a moment, it will take a time.
Yes, ma'am.
If it is done at your side, do not worry, it will happen over here.
Yes, ma'am.
Within, you can continue.
So conductivity of conductors ranges from 10 raised to 6 to around 1 ohm meter inverse. For semiconductors, it ranges from 10 raised to minus 8 to 10 raised to 3 ohm meter inverse. And for insulators, it ranges from 10 raised to minus 7 to 10 raised to minus 25 ohm meter inverse. So we know that insulators have the least conductivity and the maximum resistivity. So resistivity for conductors is 10 raised to minus 4 ohm meter. So they have very less resistivity. For semiconductors, it is from 10 raised to minus 4 to 10 raised to 8 ohm meter. And for insulators, the resistivity is very high, 10 raised to 10 to 10 raised to 20 ohm meter around. And also, before I move on to superconductivity, I would also like to give do a recap kind of thing for this equation where resistivity is equal to m upon ne square tau, where m is the mass of the electron, n is the number of electrons, and tau is the relaxation time or the time between two successive collisions, and the relation between resistivity and temperature. So when we are increasing the temperature for a conductor, the kinetic energy of the particles or electrons will increase, and then the relaxation time, that is the time which is required between two collisions between any two electrons, will decrease. And when this relaxation time decreases, so it is inversely proportional to resistivity. So as the relaxation time decreases, resistivity increases. And so the resistivity and hence the resistance, they are directly proportional to the temperature. So as temperature increases, resistivity and resistance, they increase. And when temperature decreases, resistivity and
Fine,
resistance will decrease.
fine,
Yes, ma'am.
fine. Which PPT is going on just now at your end? Number
Ma'am,
of PPT
the slide
you
with
have shared.
a relation between resistivity and temperature.
Here we may able to see your second slide only, where you have shown the conductivity and resistivity of conductors, semiconductors, insulators.
Okay, so ma'am, I'm actually moved on. I've moved on to the next slide.
You just share it again. You just share it again. Your
Okay.
PPT.
Okay, ma'am.
Yes, now it is there, but huh,
I'll share it again.
huh. Just share it and keep it in the presentation mode. Huh?
Yes, ma'am. Now is it okay?
This is not in the presentation mode still.
Ma'am, I have changed the mode, so maybe it is taking some time.
Mm-hmm. You have done it through slideshow?
Yes, ma'am.
Have you shared your entire screen, Sai? You may
No.
have shared PowerPoint present. You
Yes,
share
ma'am.
your entire screen.
Okay, ma'am.
Just remove it, share entire screen, then only that presentation will be visible, otherwise not.
Okay, ma'am.
Hmm.
Yes, ma'am. Now I have shared the entire screen. Ma'am, now is it visible?
And your mic is muted. Yes, slideshow is visible.
Ma'am, so should I continue?
Let's start.
Sai, continue.
Yes, ma'am. So this is about the relation between resistance, resistivity, and temperature. So that the resistivity and resistance, they're directly proportional to the temperature. Now, about the discovery of superconductors. So, the phenomenon of superconductivity was discovered by a Dutch physicist, H.K. Owens, in 1911. So, he was actually working with the discovery. He was actually working with some other experiments. So, his main research goal was about behavior of gases at low temperatures. But then he was working with something related to um, liquid helium to liquefy helium, and he realized that liquid helium could be used for cooling the temperatures of other materials as well. So during this experiment, he discovered the superconductivity. So here he had taken a highly purified mercury, and the temperature of the sample of mercury was reduced to very low temperatures, that was at around 4.15 Kelvin or around 4.2 Kelvin. The resistivity, he observed that the resistivity it suddenly dropped to zero, and hence the conductivity became infinite. So it was something very different and a very unique thing. So he called this phenomenon as superconductivity. So when he discovered superconductivity, he had said that only substances at lower temperatures could show superconductivity. But later on, it was found out that at certain materials like ceramics at even higher temperatures could um, show superconductivity. Mm, so superconductivity is the phenomenon in which resistance of certain materials like metals, alloys, and ceramics it is suddenly dropped to zero when they are cooled to extremely low temperatures. And superconducting materials are those materials in which resistance suddenly drops to zero when they are cooled to very low temperatures. um, for example, metals like zinc, lead, aluminium. So he had initially done the experiment using mercury, and when he found out, he later on experimented with other materials as well, like for zinc, lead, and aluminium, and semiconductors like silicon and germanium, alloys like niobium, titanium, germanium, niobium, niobium nitride, and ceramics like magnesium boride. So these are some examples of those materials which show superconductivity. Now, at we have seen that at a particular temperature, very low temperature, the resistivity suddenly drops to zero, and that temperature is called the critical temperature or the transition temperature, where the resistance of certain materials suddenly drops to zero. So this is a graph showing for a normal the change of resistivity for a normal metal and for a superconductor. So for a normal metal, as you can see, the change in resistivity with temperature is a slow change. But for superconductors, it suddenly drops to zero at this temperature, which is the critical temperature. So it suddenly comes down to zero. These are critical temperatures of some of the materials. So mercury, which has 4.15 Kelvin critical temperature. For zinc, it is 0.85. For lead, it is 7.19 Kelvin. Aluminium, 1.75. Niobium, 9.46. Niobium titanium at 10 Kelvin. And germanium niobium with 23.2 Kelvin. So we can see that for pure metals, if we consider, the niobium has a highest critical temperature, that is 9.46. So we can say that when niobium attains a state of superconductivity faster than any other pure metal. And metal alloys compared to pure metals, they have a higher critical temperature. So at higher temperatures, they can easily attain superconductivity. So here, zero electrical resistance. Now it is a property of superconductors. It is a condition in the phenomenon of superconductivity when the given material possesses zero resistance. And Owens could identify this phenomenon, and for that he performed an experiment, like not an experiment, but it was like an observation. But for that, I would like to also uh, talk about the definition of persistent current. Persistent current is a steady current which flows through a conductor without reducing its strength. So if any conductor, it possesses some amount of resistance, the current will, some amount of current will be there, and it will gradually drop with the increase in resistance. But persistent current is when the current is stays constant and it does not reduce in its strength, or it does not change its strength. So what he observed was, for around an year, he just took a semiconducting loop, closed semiconducting loop, and the persistent currents, they continued to flow through that loop without any reduction in the strength for almost an year. And experiments also suggest that they continue to do so till around 10,000 years. And this shows infinite conductivity and zero resistivity. So this was about zero electrical resistance. That is when it is the condition where the resistance of the given superconducting material goes to zero. And superconducting has various applications, like in the field of medicine and particle physics. And nowadays there is being research is being going on in how superconductivity can be used for transportation and transmission of power for distances. And more research is being going on how these superconductors can be used, because the main limitation was about the low temperatures which has to be obtained to make a superconductor. But gradually this limitation was also overcome, because certain ceramic materials, they were found to exhibit a superconductivity at temperatures around 100 Kelvin. So gradually the temperature, more research started taking place, and now iron is being studied and used for making superconductors. So that research is going on these days. So that's it. Thank you.
Thank you, Sai. Thank you very much. It was a very nice presentation, in fact. Do not keep your PPT sharing. Keep it in
Yes,
the shared mode.
yes, ma'am. Yes, ma'am.
Keep your last PPT, last slide.
Ma'am, for the zero resistance. Yes, ma'am.
Okay, fine. Oh,
Ma'am, and one more point I wanted to mention. So can I?
you can.
Critical temperature, like this process is reversible. So like when the temperature is dropped to a very low temperature, then superconductivity is obtained. Now, if we gradually increase the temperature, the superconductive, the metal or the material will gradually lose its superconducting property. So it is a reversible process.
Okay. Fine. So that the critical temperature, as Sai has said, that is the reversible process. Now, I just would like to know that as she has explained, I want to know what is a critical temperature. She has said that critical temperature, that is one of the characteristics. Here we have discussed three different characteristics of the superconductor. We know very well that a superconductor is a material which may have a very less resistance compared to any other material, whether it is in a conductor, state of a conductor, state of a semiconductor, or a state of an insulator. We can distinguish a material in three different types, that is a conductor, semiconductors, and insulators. But this superconductors is not the fourth type of the material, because you can convert a conductor into the superconductor, or a semiconductor into the superconductor, or insulator into the superconductor. So that is just a state of જમણી બાજુ પ્રસાદ આ માતાજી છે ને એની સામેની બાજુ રૂમ છે ને ક્રોસમાં ત્યાં લાગે છે ખાલી ચંડક સરને કહી દે કે આપણે સબમિટ કરી દઈએ છીએ આજે છેલ્લી તારીખ છે એટલે ખાલી એટલું કહી છે ઓકે મામા અમાઉન્ટ આવી રીતે ચાલશે. So here superconducting material, superconductivity, that is a state of a material, that is not at all a different type of a material. Is it clear to all of you? આ વસ્તુ દરેકને સમજણ પડી કે એ કોઈ અલગ મટીરિયલ નથી પણ એ મટીરિયલનું એક સ્ટેટ છે. Is it clear?
Yes, ma'am.
Now if we do have conductors, semiconductors or insulators, we know that which one is having the lowest resistance. આ ત્રણમાંથી ઓછામાં ઓછો રેઝિસ્ટન્સ કોનો હોય છે?
Conductors.
Conductors. But here these are the superconductors which are having almost so less resistance that is almost near to superconductor no કેટલો હોય છે? What is the resistivity of a superconductor? That is almost
Zero.
zero. Yes. So this is one main characteristic of a superconductor, that they do have a zero conductivity, as Sai has said over here, that zero electrical resistance. Now, if a resistance of a material is almost zero, you may imagine that how much current can pass through. If a resistance is almost zero and we are passing a current, how that current will stop? જો રેઝિસ્ટન્સ ઝીરો છે તો એ કરંટને બંધ કોણ કરશે? ફ્લો ઓફ ઇલેક્ટ્રોન. who will stop the flow of electron? સુપરકન્ડક્ટરમાં જનરલી આપણે કરંટ પાસ કર્યું કોઈ બી મટીરિયલમાં તો રેઝિસ્ટન્સ આવે, રેઝિસ્ટન્સના લીધે કરંટની વેલ્યુ ઓછી થાય. સુપરકન્ડક્ટરમાં મેં એક વખત કરંટ પાસ ઓન કર્યો.
सॉरी मैम मेरे को गुजराती नहीं आता ज्यादा.
हाँ sorry.
थोड़ा बाउंसर जा रहा है मेरे.
Superconductor, in superconductor, whenever we are passing a current, there is a zero resistance. For example, if I have a ring of a superconductor, I am making a ring of a superconductor. This material is superconducting material. I am passing a current through this ring. Potential difference मैंने दिया हुआ है. Across the ring, I had given a potential difference. And once we shall divide अपने charger. ये मेरे पास रिंग है, रिंग मैंने बनाया हुआ है, दिस इज फ्रॉम अ सुपर कंडक्टिंग मटेरियल, ठीक है। मैंने पोटेंशियल डिफरेंस एक बार दे दिया, बिकॉज ड्यू टू द पोटेंशियल डिफरेंस करंट विल फ्लो थ्रू दिस रिंग। अब करंट जब ये रिंग में पास ऑन हो रहा है, व्हाट इज द रेजिस्टेंस ऑफ अ सुपर कंडक्टर, व्हाट इज इट्स रेजिस्टिविटी? हमने क्या देखा, उसका रेजिस्टिविटी कितना है?
0.
तो उसमें जो करंट होगा वो करंट बंद कैसे होगा, कम कैसे होगा, क्या वो हमेशा चलता ही रहेगा, चलता ही रहेगा? व्हाट विल हैपन? All you students are getting my point or not?
Yes, ma'am.
साकेत, ओम, प्रीतम, आई एम आस्किंग टू ऑल ऑफ यू, मैं सबको पूछ रही हूँ, जितने जितने डिवीजन आर में है या आईसी में है या इंजीनियर्स बनना चाहते हैं, इट इज कंपल्सरी फॉर ऑल दो स्टूडेंट्स. इफ यू अंडरस्टैंड समथिंग, यू मे गेट योरसेल्फ कंफ्यूज्ड एंड यू मे आस्क समथिंग. जब नहीं
मैम
पूछ
वो
रहे हो यानी
ऑलमोस्ट
कोई
चलता ही
confusion,
रहेगा।
वो ऑलमोस्ट
तो
चलता
आपने
ही
रिंग का
रहेगा.
पूछा ना, एक
हाँ,
एक रिंग में करंट तो
Rings-
रेजिस्टेंस की वजह से वो निकल नहीं जाएगा, मतलब कम होता नहीं जाएगा धीमे धीमे।
मैं वही बोल रही हूँ, सुपर कंडक्टर का रेजिस्टेंस हमने क्या लिया हुआ है?
वो 0 है।
मैम सुपर कंडक्टिंग
हाँ
मटेरियल में रेजिस्टेंस ऑलमोस्ट 0 है, तो करंट फ्लो
Yes.
करता ही रहेगा।
हाँ, तो यानी सालों के सालों तक वो करंट वहां पे ही रहेगा. मैं कोई चीज छोड़ के गई, सुपर कंडक्टर का लूप छोड़ के गई, उसमें एक बार मैंने करंट प्रोड्यूस कर दिया, पोटेंशियल डिफरेंस दे दिया, दैट विल कंटिन्यू फॉर होल लाइफ.
इफ टेम्परेचर वो रहेगा तो ही।
हाँ, अगर टेम्परेचर क्रिटिकल टेम्परेचर रहता है तब की बात है. इफ इट इज बिलो क्रिटिकल टेम्परेचर. चलो, इससे एक चीज ज्यादा मुझे जाननी है, व्हाट डू यू मीन बाय क्रिटिकल टेम्परेचर? आप लोगों ने क्या समझा? क्रिटिकल टेम्परेचर कौन से टेम्परेचर को बताया? Sai has explained in a very well manner, but what you, all of you have understood.
When the resistance
Critical
is
Resistivity of
almost
material becomes 0.
हाँ,
Critical
critical
temperature is
temperature
the
यानी
temperature where the state is changed or a
state is
major
changed,
change
state is
arrives.
changing. हाँ, any material, any state to which state, कौन से state में convert हो जाता है material वो temperature से?
Conducting or any material से
हाँ,
superconductor.
हाँ, सही ग्राफ दिया है रेजिस्टेंस का, वो वाला स्लाइड जरा दिखाओ.
यस मैम.
तो हमेशा जैसे जैसे टेम्परेचर बढ़ता है, वाइब्रेशंस बढ़ता है, वाइब्रेशंस बढ़ने से रेजिस्टेंस बढ़ता है. नॉर्मल मेटल में हम ये लेते हैं. जैसे जैसे टेम्परेचर कम करते जा रहे हैं तो उसका वाइब्रेशंस कम हो रहा है, रेजिस्टेंस कम हो रहा है. पर एक टेम्परेचर ऐसा आता है कि वो टेम्परेचर से भी जब हम कम करते हैं, जैसे साई ने बोला कि फॉर मर्क्यूरी फर्स्ट वी फाउंड दैट इज 4.1 केल्विन. जैसे जैसे नीचे लेते गए 4.1 केल्विन पे पहुंचा तो ऑलमोस्ट रेजिस्टेंस 0 हो गया. So critical temperature is a temperature at which point the material changes its state to the superconducting state. जो temperature से वो superconducting state में आ जाता है, वो temperature को critical temperature बताते हैं. अगर मुझे material को superconducting state में रखना है, it is very much necessary for me that I should maintain that critical temperature. मुझे material का वही temperature maintain करना है compulsorily. Fine? और मटेरियल का वो टेम्परेचर मेंटेन मैं कैसे कर पाऊंगी? मुझे कोई दूसरा सिस्टम देना पड़ेगा वहां पे, उसे लोअर टेम्परेचर पे रखना है.
Yes, ma'am.
है ना? तो अगर मुझे कहीं पे भी प्रैक्टिकली सुपर कंडक्टर यूज करना है तो मुझे उसके साथ कौन सा सिस्टम चाहिए? कूलिंग सिस्टम चाहिए हमेशा
Yes,
के
ma'am.
लिए.
Yes.
दैट इंक्रीजेस माय टोटल इकोनॉमिक, मेरी जो इकोनॉमिकल वैल्यू जो है उसकी, वो टोटल इकोनॉमिक वैल्यू बढ़ जाएगी या नहीं बढ़ेगी?
बढ़ जाएगी.
है ना? हाँ. देव, would you like to say something or would you like to ask anything?
I want to ask something, मैम. जैसे आपने कहा कि सुपर कंडक्टर इज अ स्टेट ऑफ, मतलब वो चौथा कोई स्टेट नहीं है, बट वो एक मतलब मेटल का स्टेट है. तो मैम ये जैसे ग्राफ बता रहा है, तो मैम इसमें कैसे डिफरेंशिएट कर रहा है कि नॉर्मल मेटल है और सुपर कंडक्टर है? तो मैम इसके हिसाब से तो मैम सुपर कंडक्टर एक चौथा टाइप का मटेरियल है.
साई, क्वेश्चन समझ में आया?
यस मैम.
क्या होगा उसका आंसर, क्या हो सकता है इसका?
The graph is just like there are two graphs. One of them is showing this state of the normal metal. So if at normal temperature, like in normal conditions, what happens to a normal metal, and at the like for a semiconductor state. So when those conditions are being provided to that, the temperature will um, drop to zero at the critical temperature.
ओके, थैंक यू।
हाँ देखो, यहाँ पे जो आपको ग्राफ दिखाया गया हुआ है, वो हैज आस्क्ड द क्वेश्चन। क्वेश्चन किसने पूछा?
मैम मैंने, देव।
हाँ देव। सो यहाँ पे आपको जो ग्राफ दिखाया गया है, ये ग्राफ में आपको मेटल के लिए और सुपर कंडक्टर के लिए अलग से दिखाया है, क्योंकि सारी मेटल्स आप सुपर कंडक्टिंग स्टेट में कन्वर्ट नहीं कर सकते। कई मेटल्स ऐसी है जिसका टेम्परेचर आप कितना भी डाउन कर दोगे, दे विल नॉट बी कन्वर्टेड इनटू द सुपर कंडक्टिंग स्टेट। ठीक है, मैं बोलूंगी आपने इफेक्टिव मास का इक्वेशन का थ्योरी आपको करना है, आपको करना है, आपको करना है। देयर माइट बी 4 or 5 people who will be doing, but there might be others. How much I will do, how much I will tell, they will not do. So it is not necessary that all the materials will convert them their state into the superconducting state. काफी मटेरियल है जो सुपर कंडक्टिंग स्टेट में कन्वर्ट होते हैं, और मेन चीज ये है कि काफी मटेरियल्स जो नॉर्मली इंसुलेटर्स माने जाते हैं, अगर उसका आप टेम्परेचर डाउन करते हो ना, तो वो सुपर कंडक्टिंग स्टेट में कन्वर्ट होते हैं। पर काफी कंडक्टर्स है कि जो रूम टेम्परेचर पे बहुत अच्छे कंडक्टर्स है, पर उसका अगर आप टेम्परेचर डाउन करोगे तो वो सुपर कंडक्टिंग स्टेट में कन्वर्ट नहीं होते। सो दिस इज ऑल्सो अ सब्जेक्ट ऑफ रिसर्च। ये बहुत बड़ा रिसर्च का सब्जेक्ट है कि क्यों ये काफी कन्वर्ट होते हैं और काफी नहीं होते। जो कंडक्टर्स है बहुत अच्छा कंडक्ट करते हैं, उसका टेम्परेचर डाउन करते हैं तो वाइब्रेशंस कम हो जाते हैं, वाइब्रेशंस कम होकर रेजिस्टेंस कम होता है, फिर भी क्यों वो कन्वर्ट नहीं होते सुपर कंडक्टिंग स्टेट में। सो दिस डज नॉट हैपन टू ऑल द मटेरियल्स। For a certain materials only, when you take that temperature down, the resistance will become almost zero, and at that time they will be converting themselves into the superconducting state. ठीक है, तो सबसे पहली चीज सुपर कंडक्टर का सबसे पहला कैरेक्टरिस्टिक आप नोट डाउन करके रखना। आई विल आस्क टू ऑल ऑफ यू वंस अगेन व्हेन आई विल स्टार्ट विथ जीरो रेजिस्टेंस, यानी कि रेजिस्टिविटी उसका ऑलमोस्ट जीरो है। सेकेंड थिंग क्रिटिकल टेम्परेचर, यानी एक मिनिमम टेम्परेचर ऐसा है कि जहां पे वो सुपर कंडक्टिंग स्टेट में कन्वर्ट होता है। एंड थर्ड दैट अबाउट द करंट, जैसे मैंने बोला कि मेरे पास ये लूप है, लूप में अगर मैं करंट दे देती हूँ, सुपर कंडक्टर का लूप है तो वो कंटिन्यूस चलता रहेगा, तो ये क्या ये करंट लाइफ टाइम तक चलता रहेगा? मुझे ये बताओ। साई ने बोला यहाँ पे पीपीटी में, साई लास्ट वाला पीपीटी आपका दिखाओ। साई उसमें आपने बोला कि कुछ साल तक चलेगा, कितने साल आपने कुछ बताया? 10,000 समथिंग। हाँ, 10,000 ईयर्स। हाँ, वो क्यों 10,000 ईयर्स तक चलेगा? बाद में कैसे वो बंद हो जाएगा?
Ma'am, it was like if the given conditions are like if the conditions are maintained for the temperature, like if it lies below the critical temperature only, so there is no resistance, so the it will be infinite conductivity and फिर वो चलता रहेगा. But if there
So
is
I am
some
maintaining that condition
Ma'am, I
throughout
have
the
an
life.
answer. All. Ma'am,
Just a minute, just a minute, just a minute. साई अगर थ्रू आउट लाइफ में ये मेंटेन करती हूँ
yes ma'am,
सिस्टम,
yes ma'am,
what will happen in that case?
After a very long time, maybe it will slowly start reducing, but otherwise the
Due
conductivity will.
to which factor it will start reducing? Vaibhav, you may rejoin again. Dev, you said that you have answered.
no, ma'am, I said.
Who said?
Muhammad.
I don't know. Yes, tell me. Who is going to give answer?
Ma'am, we have said that the resistance is almost zero, not a zero, almost. So we have some resistance there.
Yes, is it
So
Muhammad?
yes,
हाँ, देखो साई आपने भी बताया रेजिस्टेंस इज ऑलमोस्ट जीरो, नियर टू जीरो, दैट इज नॉट एग्जैक्टली जीरो, है ना? तो कुछ रेजिस्टेंस तो है ही है, भले बहुत कम वैल्यू है. So to all of you, the current which we are flowing through the superconductor, ring of a superconductor, it will remain there for so many years. But maybe it will decrease at some point because minor resistance is there, that is near to zero. पर वो सालों के सालों तक वो करंट ऐसे ही मुझे मिलेगा. पर कुछ साल के बाद जैसे यहाँ पे बताया 10,000 after 10,000 years, after 1 lakh years, like that it will decrease. So that is correct, as Muhammad has said. Yes.
Sorry to interrupt, but our BE lecture link is already there.
Now it's
So
time has gone up. Okay, so I would like to wind up the session by telling three things that today we had seen a characteristic of the superconductor, that is a zero electrical resistivity, persistent current, that's persist there, persist એટલે જળવાઈ રહ્યું, to stay there, persist means. And third thing, that is the critical temperature. Is it clear to all of you? આ ત્રણ characteristic superconductor ની બધાને clear છે?
Yes, ma'am.
Yeah, ma'am.
Fine. And Sai, that was a very nice presentation. And who else can give now? Who else is ready to give presentation? Yes, Saket is ready. Fine. So Saket, next topic I am sharing on the group. So keep your topics ready. And Sai, very good initiative, I must say. And PPTs are also in a very presentable mode.